Welcome, everyone. I am so thrilled you're here at the exhibit today for this explainer. We're going to be diving into a genuinely fascinating scientific journey based right off the poster we have here. We're looking at the hidden world of concrete, specifically this massive push to replace traditional cement with something called quarry dust. It sounds simple enough, right? But trust me, the chemistry and the timelines involved are absolutely captivating.
Okay, let's dive right into this and get a quick roadmap of what we're covering today. We've got Section 1, the concrete dilemma. Then, formulating the experiment. Moving into the early strength surprise, followed by the long-term reality. Next up is the statistical proof. And finally, we'll wrap up with the final verdict.
So, Section 1, the concrete dilemma. Let's set the stage.
If you take a look at the poster we're showcasing, you can really see the big picture. Concrete is, well, it's arguably the most versatile and vital structural material in all of human history. But there's a catch. Its main binding agent, cement, has a massive, and I mean massive, environmental and carbon footprint. So the researchers behind our exhibit set out with one very specific goal: to investigate quarry dust. Now, quarry dust is essentially this superfine waste byproduct left over from crushing rocks. They wanted to see, hey, could this act as a sustainable partial replacement for all that carbon-heavy cement?
Which brings us to Section 2, formulating the experiment.
To figure this out, the lab methodology had to be incredibly precise. Here's the exact recipe they used. The baseline mix was pretty straightforward: 1 part cement, 2 parts fine sand, and 4 parts coarse gravel. And this is absolutely crucial. The water-to-cement ratio was strictly locked in at exactly 0.60 across the board. No variations there. To run the test, they swapped out some of the ordinary Portland cement with finely sieved quarry dust at very specific intervals. So we've got a control group with 0% replacement, an experimental group at 10% replacement, and a third group at 20%.
Once those different mixtures were poured into their cylindrical PVC molds, the real chronological testing kicked off. Because, concrete doesn't just dry like paint, it actually cures and chemically matures over time. Using a universal testing machine, the researchers systematically crushed these concrete cylinders at 3 distinct checkpoints: 7 days, 14 days, and then the ultimate 28-day mark. And that schedule? That basically forms the whole timeline for the mystery we're about to unpack.
Moving right along to Section 3, the early strength surprise. Now, what's really interesting about this is the totally unexpected anomaly we see at that very first 7-day check-in. You'd probably assume that the mix with pure, unadulterated cement would be the strongest right out of the gate, right? I know I did, but it wasn't. The standard control baseline hit a mean compressive strength of 5.6 megapascals. But look at this. The 10% quarry dust mix actually beat it, hitting 5.9 megapascals. Now, the 20% mix did fall behind at 4.1, but that 10% spike, that is a huge, totally unexpected initial victory.
So why on earth did that happen? Well, it boils down to something called the physical filler effect. Think of it like this. Imagine a jar full of large pebbles. If you pour fine sand into that jar, it fills up all those empty air gaps, right? It makes the whole structure much denser. That's essentially our microzoom analogy here. The quarry dust particles were sifted through an ultra-fine 0.150 millimeter mesh. In those early days, these microfine particles packed perfectly into the microscopic voids inside the fresh cement paste. This completely densified what's called the interfacial transition zone surrounding the larger gravel, which rapidly accelerated the concrete's ability to resist early loads. It's kind of like a structural shortcut.
All right, Section 4, the long-term reality. As awesome as that early strength boost is for sustainability, we have to look at what actually happens to the concrete as time marches on and those early benefits start to fade. Let's put that initial 7-day win side by side with the ultimate 28-day reality. By day 28, the dynamic totally flips. The standard control mix pulls way ahead, finishing at a high of 10.7 megapascals. But that 10% mix, our early winner, it actually drops 19.63% in strength, finishing at just 8.6. And the 20% mix? Man, it plummets even further, dropping almost 32% compared to the control, bottoming out at just 7.3 megapascals.
But abstract numbers really only tell half the story. Look at these visceral images straight from the lab of the destroyed concrete cylinders. The profound cracking and ultimate crushing you're seeing here is the direct physical result of what we call the dilution effect. See, quarry dust is mostly just an inert mineral. It's not an active hydraulic binder like real cement. So when you swap cement for dust, you are quite literally diluting the mixture. You're starving the concrete of crucial compounds, specifically tricalcium and dicalcium silicate. And those are absolutely essential for long-term calcium silicate hydrate gel production. That gel is the literal chemical glue that gives concrete its ultimate structural strength.
If we zoom in a bit closer on the structural damage, you can clearly see these incredibly rough, fractured internal textures. There's a very specific physical reason it failed like this. Quarry dust has a super sharp, highly angular shape compared to standard rounder materials. This jagged shape drastically increases internal friction, and worse, it acts like a sponge, increasing the water demand in the fresh mix. Remember how they strictly locked that water ratio at 0.60? Well, because this angular dust soaked up so much of that available water, the mix became much harder to work with. This led to microscopic empty pockets forming when they packed it into the molds, and those microvoids became severe internal weak points that ultimately crippled the concrete's load capacity.
Which leads us to Section 5, the statistical proof.
Now, any good researcher is going to ask, are these strength drops just random flukes from mixing the concrete by hand? So the crucial point here is this massive percentage, 99.9953%. To make sure the data was absolutely rock solid, the team ran a one-way analysis of variance, an ANOVA test, and they got an exceptionally low p-value of 0.000047. In the academic world, that is literally light years below the standard threshold. This number is essentially the ultimate judge's verdict. It proves mathematically, with near absolute certainty, that these drops in strength weren't just some lab error. Changing that cement replacement percentage causes a genuine, reproducible, and permanent loss in the concrete's ability to hold weight. No way around it.
And finally, Section 6, the final verdict. Let's bring all this microscopic physics and heavy data back to the big picture for the industry. We started out looking at the poster for this exhibit, hoping to find the perfect, sustainable replacement for heavy polluting cement. And what we found was that while quarry dust gives us this incredible packing-based strength boost in the very early days, the hard physical limits of the dilution effect eventually take over, severely compromising the long-term durability. So it leaves us, and really the entire construction industry, with a profound, real-world trade-off. Knowing these physical limits, where do we draw the line between sustainable waste disposal and vital structural integrity? It's a delicate, absolutely crucial balance we have to strike if we want to build a greener future that won't literally crumble under pressure. Thanks so much for walking through this explainer with me today.